Okay, so to understand the equations of planes in 3D, well, planes are always 3D. You always draw planes in at least a three-dimensional space. But if you're going to understand them, you really need to know something about vectors, because it's super hard to study surfaces without vectors. It's very, very difficult. All right, so the first thing you have to understand is how to do a dot product. You have to know how to do a dot product, and it's very simple. You just take A dot B, or A, B, C dot D, E, F like that. And you do this by multiplying the A with the D, the B with the E, and the C with the F, and adding. The result is a number, a scalar. It has no direction. It's just a number, like 14. Kind of like when you do determinant of a matrix, right? Okay, the other thing you need to know how to do with two vectors is do a cross product. Or some people call it a vector product, because the outcome is actually a vector result. Okay? So here's how you do a vector product or a cross product. Here's how I do it. Okay, some people memorize a real long formula. I write I hat, J hat, K hat as my first row of a 3 by 3 matrix. And then inside, I put in the vector ABC on the first, well, technically the second row, and DEF on what's our third row there. So the top row is, these three guys basically mean, they're all unit vectors, okay? And they point in the directions x, y, and z respectively, okay? So an I hat literally looks like this. I'll draw it. If this is your x-axis, and this is x equals 1, I hat points one space in the x direction, okay? All delta x's, all translations in the x direction are made up of I hats. Okay? For example, one I hat will take you one space. Two I hats will take you 2 spaces. 3 I hats will take you 3 spaces. And not just from the origin, from wherever you're at. Okay? So I guess I hat's job is to advance you one space in the x dimension, positive x dimension. If you do like a negative one I hat, you go backwards in the x direction. J hat's job is to direct us along in the y direction. K hat is sort of, for the z. So IJK corresponds to x, y, z. Okay? Just know that these are normally numbers, A, B, C, D, E, and F, but the I hat and the J hat and the K hat are not numbers, and they stay in your work throughout the work. Okay? So you do this by doing a determinant. First you write down I hat, and then you'll find the determinant of B, C, E, and F. So basically these 4 right here. Okay? Then you go to minus. There's a mandatory minus here. And then you do J hat next. Now for J hat, you're going to be working with actually these 4 values and doing a little determinant AF, AC and D and F. See? So you use everything but what's in the J column, actually. So just the things that are not in the J column are used, you see. And then lastly, the K. This third term is positive here. So I guess you could say altogether it goes plus, minus, plus. The last one is K, and I write my K's in cursive. So even though I know cursive starts with C. I know cursive starts with C, but I write my K's in cursive. Let's use these 4 values then. A, B, and D, and E, see? And you know how to do a 2 by 2 determinant. You just basically multiply and subtract, multiply and subtract. So this part here is BF minus CE. And this part here is AF minus CD. And this part is AE minus BD. You see? Okay, so it's all very messy, but when you're using numbers, it's not messy at all. This comes out real nice, 5 I hat minus 2 J hat plus 10 K hat. Okay, now when you get an answer that's just 0, 0, 0, then that means that you didn't have a very interesting result, okay? But most of the time you're going to get something like, 2, negative 5, 10, or something. And when you get a non-zero vector like that, know that this answer is another vector. Okay, this is very, very important you understand this. So what I'm trying to say is you're going to get a vector answer to this thing, specifically BF minus CE, the opposite of AF minus CD, so CD minus AF is what happens here. And you're going to get an AE minus BD here. These are 3 numbers, and they represent a vector. And what's unique about this is the vector U and the vector V, when you find their cross product, what happens is you create a third vector called U cross V. It's probably even longer than U and V are. And it points in a direction perpendicular to both of the originals. Okay? So it'd be kind of like if these 2 markers, these 2 colored markers, were my original vectors, U and V, let's say. When I do a cross product, it creates this stick. This stick's a little too long, it's exaggerated. But it creates another vector, and it points in some direction perpendicular to the 2 colored markers. Okay, now, it doesn't matter what the angle is between these 2 colored markers as long as it isn't 0. So like if this angle between these 2 colored markers is very, very tight, the only thing that happens is this vector is shorter. So this vector is like little, like that. But it still is perpendicular. Even if these 2 colored ones are not perpendicular, this new one, the cross product vector, is perpendicular to both of these. It's perpendicular to the blue and the red, you see. The way you make this third vector the longest possible is when you pull these to make a right angle. So if you make the red and blue into a right angle, what happens is you get the longest possible third stick coming out. So that would be like this case. These cross product vectors are quite long when the original 2 were already perpendicular. If the original 2 are not perpendicular, that just makes this shrink a little bit. Okay? So what I'm trying to say is, if you're ever standing on a surface, okay, which you are most of the day, standing on a surface, right? And you pick any 2 vectors that are laying down in that surface. Like maybe you pick up a pencil, there's a pencil laying on the ground, that's a vector, right? You got another pen laying over there. If you cross product those, then whatever vector results from that is going to be sticking up out of the ground. So if there's 2 pens laying on the ground, even if they're not touching, if you bring their tails together, you check that angle between them, there's a third vector pointing straight up out of the ground, or maybe straight down into the ground, depending. And that vector has a length dependent on the angle between the 2 pens that you found on the ground. Okay? Sometimes those vectors point up out of the ground, sometimes they point down into the ground. But these vectors are called normal vectors. They are normal to the plane. Normal means perpendicular. So, perpendicular to the plane that you are studying. Perpendicular to the plane that contains U and V. Okay, how many of you already knew this knowledge? Like, you already had this knowledge? Okay, so it's a physics thing, because we use vectors all the time in physics, but it isn't actually only physics. Math uses it too, and it's not that hard to do, and it's really not that hard to understand. Imagine 2 arrows coming together, and if you do a cross product, you get a third one perpendicular to those 2. Okay? All right. Now, our goal today is to find the equation of a plane. Okay? So, you basically needed to have those 2 skills just to do anything at all. Like, you can't do any of the mathematics today at all unless you know how to do those 2 rules I just showed you. Let's talk just geometrically about planes for a minute. So Euclid said, if you're going to have a plane, if I'm thinking of a plane, and I'm trying to describe it to you over the phone, let's say, I need to give you 3 points. There's no way on earth you can guess what plane I'm thinking of from only 2 points. You need 3, okay? And those 3 points better not be in a straight line. Here's what I'm saying. If this is your desk, right, and you're trying to describe a plane to somebody, you might pick this point, and let's say there's a cup on your desk over here. You might pick this point on the cup, okay, and then here's you sitting here. you might pick your nose, okay? You just gave me 3 non-collinear points. 3 distinct points. They're not in a straight line. And obviously, spatially, there's a triangle that can connect these, right? And as long as there's a triangle that can connect them, then that triangle must exist on one plane. A triangle is a flat shape, after all. So this triangle that I'm shading right now lives on a particular plane, and that plane is very clearly defined by these 3 points. If you give me more points, that's just icing on the cake. You don't need it. It also might be that the 4th point you give me isn't actually on the plane, okay? This is why desks with 4 chairs tend to wobble, but a 3-legged stool never wobbles. It can't. It's impossible for a 3-legged stool to wobble. Think about it. The 3 legs on the stool, right, can only live in one plane, the tips of those 3 legs. And that plane is the floor. Okay? As soon as you add a 4th leg, you get wobbling. So tables wobble, desks wobble. I don't know why we don't make more 3-legged objects, because they never ever wobble. I think it's for stability reasons. A round table with only 3 legs could be tipped over if someone puts their elbow on it too hard, you know? You see what I'm saying? But so they build it for stability, but in terms of like wobbling, 4-legged tables are notorious for it. Okay? And it's because one leg might be shorter than others, and then you have that problem with that 4th point being off the ground or whatever. Okay, so this is a minimum scenario, but it's also a sufficient scenario. It is necessary, you have to have 3 points, and it's sufficient, don't give me more. You can also do it by having just 2 distinct lines. For example, if I was telling you, hey, I've got, I'm thinking of a plane, and I'm trying to kind of show it to you, so I hold up 2 markers, you know, like this, parallel markers. Well, they're parallel, so you can see from the edge they can live in the same plane, you see. 2 parallel markers can be set simultaneously on a desk, for example, which might be our plane. So 2 parallel lines would be sufficient. You told me the equation of 2 parallel lines. I've got myself a plane, and I can tell you where it is. 2 distinct intersecting lines would also be sufficient. In other words, they don't have to be parallel. It can be just crossing lines. So if you had 2 markers that were crisscross like that, whoop, that represents one flat sheet in space. Okay? These are all things Euclid said long ago, and he's right. Okay, here's the next thing that you may or may not know. One vector that is in the plane, or at least parallel to the plane, and 1 point in the plane. And 1 vector normal to the plane, and 1 point in the plane. So this is a little bit harder to understand. This would be sufficient for me to give you this perpendicular vector and this point. So as long as I told you, hey look, this vector is not pointing in the direction of the plane. It's perpendicular to 4. And you're like, okay, I want to make a plane now. Well, if they gave you those 3 points, you can be sure that subtracting any 2 of them will give you a vector in that plane. Right? So, for example, PQ might be the vector, well, it will be the vector x1 minus x0, y1 minus y0, z1 minus z0. That vector should be in the plane, or at least parallel to the plane, because it's made up of 2 points in the plane. Same thing with PR. PR would be x2 minus x0, y2 minus y0, z2 minus z0. These vectors are laying in the flat in our plane that we wish to study. Since these vectors are both in, or at least parallel to the plane we wish to study, we can create a vector that's perpendicular to them by cross-producting them. So finding a cross product. Remember we said the cross product will give us a third vector perpendicular to both of these? Okay, and our goal is to create 1 vector normal to the plane. So we want to take the cross product of these 2. I wrote the determinant here for you. The outcome is a horrible mess. Okay? We'll write it, but we'll probably run out of room, and I'll probably just get frustrated and start scribbling. Okay, so here's what it's going to look like. You start with I hat, and you basically multiply y1 minus y0 and z2 minus z0, y1 minus y0 times z2 minus z0 and then you subtract z1 minus z naught times y2 minus y naught. So z1 minus z naught times y2 minus y1, I think that says. I think it says y1. No, why not? Why not? Okay. And that's our first component. It's followed then by a minus sign, as I mentioned earlier. And then we get on to the j. And for the j, we're going to be using these four. Everything that isn't in the j column. So basically it's x1 minus x naught, z2 minus z naught, minus, and then z1 minus z naught, x2 minus x naught. And that's our second component. And there's still one more that I haven't even started on yet. Do you want me to write it or not? Yes. Okay, I'm out of space too, but I'll write it in green. It's going to go plus k hat, and you'll be using these four elements of your matrix right here. So it should look something like x1 minus x naught, y2 minus y naught, minus y1 minus y naught, x2 minus x naught. So it's a jumbled mess. But when the values are in here, and the x1 is 2, and that sort of thing, it all cleans up real nice, okay? But it will give us that vector that we desire, one of the ingredients for a plane. And how would you describe this vector compared to the two vectors PR and PQ? This long, long answer we just wrote, how does it fit geometrically with the two in this box up above it? It's perpendicular to both of these. Okay. So at that point we'll know three vectors, two that are in the plane and one that is perpendicular to the plane. Okay? So although this is quite messy with variables, it's relatively simple when values are plugged in. And we're going to call this answer for now, because I'm too lazy to write all that stuff. I'm going to write it as nx, ny, and z. N means normal or perpendicular. If you're in physics, this is the meaning of normal force. It means perpendicular to the surface of contact. Okay, so once we have this normal vector, we can assume it is orthogonal or perpendicular to every single vector in the plane we're studying. Because it's like, if this is the ground and this is a flagpole, the flagpole is perpendicular to every possible vector you could ever find on the blue plane. Every pencil that was dropped, every segment on this plane, every vector on this plane is perpendicular to that flagpole. See? Okay, now we need one more thing. What was the requirements for this condition? We needed one vector normal to the plane and one point in the plane. We have all that. So we're going to pick, we want our point to be random though. Okay, we don't want to pick the P and the Q and the R they gave us. Those are fixed points. No good. We want our equation for the plane to have x, y, and z in it. We don't want them to have all numbers. So we're going to pick one more point in the plane. We're going to call him x, y, z. Okay? And so the vector pk would be this. Watch close. X minus x naught, y minus y naught, z minus z naught. X, y, and z are truly variables now. X naught, y naught, and z naught are still numbers. Okay, so pk is this brand new vector we just created. N was the horrible vector on the previous page, that really long one. And one thing you need to know about a dot product. When you find a dot product, if you get 0, it means that your vectors were perpendicular to begin with. So since we expect pk, which is in the plane, and n, which is perpendicular to the plane, to be perpendicular, we expect vector pk and vector n to dot to 0. And this is the key to the whole lesson right here. Since we know that a normal vector dotted with any vector in the plane is 0, we know that in x, in y, in z, remember I was too lazy to write out the long version of that, this dotted with x minus x naught, y minus y naught, z minus z naught, let me rewrite this, should be 0. So we have n sub x, n sub y, n sub z, dotted with x minus x naught, y minus y naught, z minus z naught. When you do the dot product, you multiply these together, you multiply these together, you multiply these together, and you just add them up. So here's the answer. This is the equation of a plane. Ready? N sub x times x minus x naught plus n sub y times y minus y naught plus n sub z times z minus z naught. And this is called the scalar equation of a plane. So I'm sorry for the long derivation, but this is the equation of a plane. Now it's time to do an example. And they are very easy. Okay? It's always about getting that equation. That's the hard thing. Then you memorize it and you use it. Hopefully you're not asked to rederive it, But hopefully what I did made some sense to you too. Although the first time might have been totally mysterious. Okay, let's try this problem down here now. Now we're getting into the real examples. I'm given 3 points. They are specifically 2, 3, 4, negative 5, 1, 8, and 6, 7, 0. First thing I'm going to do is find vectors PR and PQ. Okay? Let's get busy. Actually, why don't you guys do it? PR and PQ. So remember, when you find vector PR, you're supposed to do point R minus point P. So head minus tail. So the second letter is R. You'll do that first. You do R minus P, and that'll give you the vector for PR. And then do the same thing for PQ. You do it in your head. Very easy. I'll show my work. 6 minus 2, 7 minus 3, 0 minus 4. I'm getting 4, 4, negative 4. Did anyone get that? Okay, let's do PQ now. Negative 5, take away 2. 1 minus 3. 8 minus 4. I got negative 7, negative 2, and 4. Does that look right? Okay. Now if we take the cross product here, I already set up your determinant for you. You're going to get the vector n. Then we're going to dot it with x, y, z, and we'll be done. It'll be easy. Okay, so first we do... I'm going to skip all the IJK garbage. Here's the goal, watch. Use these 4 numbers and do a determinant. You can do it in your head. This product is 16, this product is 8. Subtract. What's 16 minus 8? 8. Okay? Now this is the first entry, so don't change its sign. So that was 16 minus 8. I'll write above it how I got it. Okay, let's look now at the J component. That's basically using these 4 numbers. Same exact game. Now it's 16 minus 28. 16 is 4 times 4, and the 28 is the negative 4 times negative 7. So what's 16 minus 28? Negative 12. But because this is the middle term, we're going to negate it. You always switch the sign of the middle term in a determinant if you're using the first row for expansion, or even this third row, really. Okay, now let's go. Oh, so that was done by using the opposite of 16 minus 28. Okay, and then the last one, you'll be using these numbers here. This time it's negative 8 minus negative 28. So it's negative 8 and there's negative 28 and you're subtracting. So it feels like you're adding that negative 28. So you add the 28. You end up with basically negative 20. Is it negative 20 or positive 20? Positive 20. And we're not going to change the sign because you only do that on the middle term. Okay, so this was calculated by doing negative 8 minus negative 28. Yeah, 20. This is the vector. 8 is one of the vectors that's perpendicular to our plane. Okay, so here we go. We're going to take 8, 12, and 20. We're going to dot it with x minus x naught, comma y minus y naught, comma z minus z naught. And as for which point we are going to choose for x naught, y naught, z naught, we can pick any of the original 3 points. It doesn't make any difference. So far in my work, I've been kind of treating point P as sort of the, the tail of everything, the tail of all the vectors. So I'll go ahead and pick that again. I'm going to put the 2, 3, and 4 in here. Again, those are the coordinates of point P, but you really can use any point you wish. Okay, so the dot product, remember, is where you take the x components, you multiply them. You take the y components, you multiply them. You take the z components, you multiply them. Then you just put them all together in one big string. So the answer is 8 times x minus 2 plus 12 times y minus 3 plus 20 times z minus 4 equals 0. And that's the answer. If you want to, you can go ahead and divide, like the coefficients a little. Like you'll notice 8 and 12 and 20. These are all divisible by 4. So you could kind of reduce it a little bit. Divide everything by 4. So this is now 2. This is 3. And this is 5. But this is the equation of a plane. Now watch very closely how you read it. Listen, this is so important. Don't miss this. If somebody gave me this equation, I would know instantly what it means. The 2, 3, and 4 represent one of the many, many, many points on the sheet. Okay? Everybody with me? The 2, the 3, the 4. The 2, the 3, and the 5 represent the vector perpendicular to the plane. The vector 2, 3, 5 is the flagpole, if you will, sticking out of the ground. If that makes sense. And the 2, 3, 4 is the point that the flagpole is attached to. You can think of it that way. It's a great way to think of it. So imagine a point whose coordinates are 2, 3, 4, see? And a vector sticking out of it whose components are 2, 3, 5. Well, we know where the plane is because we know where the bottom of the flagpole is. We know the direction of the plane because it's perpendicular to the flagpole, and we've got the plane. So that's how you read this. Every number has meaning. We always desire that in a standard form. We always want every number we write to have physical meaning. It's like everything, all the ingredients there. Every number has a meaning. Okay? All right, how many of you are tempted to distribute now? Yeah, do it. Go for it. Distribute it, please. Distribute the 2, distribute the 3, distribute the 5. In fact, let's get the constant on the right side, because that's honestly the most common way you'll see an equation of a plane. So go ahead and do that. Go and distribute the 2, 3, and 5, leaving only x, y's, and z's on the left. Write your equation of the plane. And maybe you guys can tell me what you got there.
Would it lose meaning if you did that?
It loses a little meaning. Yes, it does. Unfortunately, though, this is how most planes are handed to you on a silver platter. They'll give them to you looking like this, which means you don't get as much info from reading it. What was the number on the right?
33.
That's what I got too. So 33. But see, that 33, when you look at the equation of a plane, maybe you knew this was the equation of a plane. That should be a 3. The 2, the 3, and the 5, not 2, 5, 5, but 2, 3, 5. See, the 2, 3, 5 still has meaning. That's the direction of the flagpole, But the 33, it's like, people don't know how to interpret that. What does that even mean, the 33? Well, it's a good question. This form isn't really that great. And so you have to kind of learn to unravel these too. How? Yeah, that's right. So one common way to write an answer is like this, actually. Where A, B, C, and D are real numbers. But what does A, B, and C mean? And what does D mean? Let's find out. So returning to the scalar equation of a plane, you can see that if you distribute this, you get nxx minus nxx naught plus nyy minus nyy naught plus nzz minus nzz naught equals 0. And if you take just the yellow terms over to the other side, these terms are numeric. These are numeric. The others are variable terms. So the left side is n sub xx and n sub yy and n sub zz. But the right side, I'm moving the three yellows over, n sub x naught plus n sub y naught plus n sub zz naught. Or you could write it this way, nx, ny, nz dot xyz and the right side, n sub x, n sub y, n sub z dot x naught, y naught, z naught. So what does the left side actually mean? Well, evidently, it's the dot product of the flagpole and a generic xyz vector. And what does the D represent? Well, the D evidently represents just the flagpole dotted with a random point. No. One specific point. So this is like vector n dotted with a random point, and vector n dotted with a specific point. Evidently that's what it means. We just sort of dissected it. So here's our next example, and I'm going to finish this lesson after you leave, so please watch the last few minutes. There's no worksheet for this tonight, so you'll get your worksheet for this tomorrow night. Okay, so let me show you how to do this quick example. I'll finish it after you leave. So your job tonight is to watch the video, the ending for you. Period 1 has to watch the whole thing. So get some pop. Okay, so this problem is really easy. So I'm giving you a vector and a point. So notice the difference. The vector has the sharp edges there, and the point has the curled brackets, right? Okay, so you're basically going to say, all right, here's how I get my equation of a plane. The A, B, and the C are the values for this plane are basically 1, -2, 6. So you already know it's going to be 1x minus 2y plus 6z equals something. The right side, you're going to take the vector 1, -2, 6, and you're going to dot it with the vector -4, 5, 3. And this gives us, if you do the little multiply and add sort of thing, you get -4 minus 10, and lastly, plus 18. Which just comes out to 4. That's the right side. Wow, don't you wish it was that easy? Always, there's our answer. Okay? So there you have it. I told you it was going to get easier as we got through the lesson. Hopefully you weren't too intimidated by the opening facts. Okay, this one takes a little more critical thinking. We're talking now about plane B, and there's the equation given. Notice the y components, or the y is missing, so that just means it's just only parallel to, basically y can be anything you want it to be. And so graphically, I'll let you think about kind of what that looks like. But you're going to now look at this here. This is the equation of a line. Equation of a line. So I'm trying to mix lessons 2 and 3 together. See, lesson 2, we learned that r of t is x naught, y naught, z naught plus TABC. Remember that? TABC. And I'm telling you that this is our vector right here. This is given. This is our vector. So basically x is negative 1 plus, let me rewrite that, x is negative 1 plus t, which means that this is really a negative 1, and this is a 1. So there's your negative 1 plus t. Y is 2 minus 3t, see, which kind of forces this to be a 2. That's one option anyway, to have a 2 there. And then this is a negative 3. And lastly, we have z equals 5. So this would be a 5. And since 5 is like 5 plus nothing, this is a 0. Okay, so the equation of the line is basically negative 1, 2, 5 plus t times 1, negative 3, 0. Does that make sense? Okay, so I kind of looked at the parametric equations. That's these ones here. They were given. And I rewrote it back into vector form. Okay? So I just wanted you to see how that line fits into lesson 2 there. Okay, but let's just read the question carefully and see what they're really asking. They just want to know if plane B is parallel to W, normal to R, I'm sorry, I should say parallel to R of t, or normal to R of t, or neither. So I don't know why I put W there, sorry. So the question is this. It's very simple. There is a line in space. Its name is R of t. Okay? There is a plane in space. Its name is B. We actually have the equation of this plane. It's 2x minus z equals 5. The question is very simple. Are the blue and the red parallel? Yes or no? Are the blue and the red perpendicular? Yes or no? Okay? All right. So in the end of this problem, we're going to find that the answer is actually no, no. It's not parallel nor perpendicular. So how do you do that? Well, remember on the scalar equation of a plane, the left side is basically vector in, x in x, in y, in z, dotted with generic x, y, z, variables, x, y, z. Right? And we already know that this particular plane has this equation. So I'm going to write it above it here. It's 2x plus 0, y minus 1, z is equal to 5. Right? So if you look very closely at it, you see that these three represent the vector n. See? So that vector is the 2, 0, negative 1 vector. That's sort of the flagpole in my analogy, So now we've turned this problem into, look, there's a blue plane, B, and there's a flagpole sticking out of it. And we know that flagpole's vector direction is 2, 0, negative 1. And then there's this line that we wish to study called R of t. We haven't gotten to that yet, really. And we just want to know, remember the question was, is the red vector parallel to the blue plane, which now can be reinterpreted as, is the red vector perpendicular to the blue line? See? The flagpole, is it perpendicular to R of t? Because if it is, that means that the plane will be parallel to R of t. If the blue flagpole is perpendicular to R of t, then the plane down at the bottom is going to be parallel to R of t. Okay. Okay, so the first thing we're going to do is check to see how the blue vector and the red vector work together. If we believe that these are perpendicular, right? If there's a nice right angle right here in black, I'm drawing this right angle. If this is a right angle, then the dot product will be 0. The dot product will be 0. Okay? Now a minute ago I already had you write out R of t. I don't know why I erased it. But it was basically negative 1, comma 2, comma 5 plus t abc, where this is 1, negative 3, 0. So our vector, our line, the line up here, points in the same direction as negative 1, 3, 0. Okay, so we're going to steal negative 1, 3, 0, which is sort of the direction of our red line. We're going to dot it if L is parallel to n. I'm sorry, if I'm going to cross them. If L is parallel to n, that's these blue and red vectors, then we would expect for their dot product or their cross product to be 0. If they're parallel, the cross product will be 0. So we're going to take L cross n and expect to get 0. If they're perpendicular, then we would expect their dot product to be 0. Okay, so let's check first to see if they're parallel. Okay, so we're going to take I, J, K, and 2, 0, negative 1, negative 1, 3, 0. And doing a cross product, you basically get, this is a little bit of work, but you do when you use the four numbers in the corner, you get 0 minus negative 3. So it does take a little practice to get used to this. And there's a mandatory sign change on the middle term. And then the second term of the cross product is 0 minus 1, basically, so minus 1. But that was already negated, so this becomes a plus 1. You'll have to convince yourself of that middle value there. And the last one is basically 6 minus 0, so 6. So 3, 1, 6 is our cross product vector. I would have expected, if these were parallel, the cross product would have been 0. Remember I talked about how if you have two vectors pointing the same way, or roughly the same way, the cross product vector is quite small, remember? And if you put these vectors u and v completely together and you squish the angle between them to be 0, the cross product vector just vanishes entirely. So it becomes the 0 vector. Since I didn't get the 0 vector, I didn't get 0, 0, 0, that means that the vectors are not parallel. Right? Because I ended up with, oh, here I show my work, I realize now. I'm showing all my work from my previous steps. Yeah, so this is a 3, 1, 6, is what I had a second ago, which is not the 0 vector. This means that the line RFT is not perpendicular to the plane. You may say, what? You just showed that they're not parallel. When I was talking about not parallel, I'm talking about the blue vector. So go back to this picture up here. This yellow picture up here. In this picture, we've just proven that the blue vector and red vector are not parallel. That means that the blue vector, or the blue plane and the red line are not parallel. I said that wrong. I'm sorry, I said that wrong. The blue vector and the red vector are not parallel, which means that the blue plane and the red vector are not perpendicular. Okay? All right, now we're going to test for orthogonality between L and N. This is a lot easier. So you're just taking 1, 3, 0 and 2, 0, 1, and you're doing a dot product. But this unfortunately comes out to 2, which is not 0. That's not 0. So but the fact that we didn't get a dot product of 0, that means that these vectors were not perpendicular either. So these vectors are not perpendicular, which means the line is not parallel to the plane. Okay, so maybe my yellow picture didn't help you a whole lot. Maybe it confused you more. Let me show you just roughly with two drawings what we're proving here. So in the first place, we were trying to see if the flagpole, which is sticking up out of the plane, we were trying to see if the flagpole was parallel to the line. So here's the red line, RFT, this is kind of a new drawing. If the flagpole and the line are parallel, then naturally the red line would poke through the plane at a right angle the way the flagpole does. Well, we showed that that's not the case. Okay? So we show that this is not happening. We did that by showing that L cross N is non-zero. L is a small red vector pointing in the direction of this red line. I chose L for line. Okay? And L was this vector up here. Okay, so you could spend a good 10 minutes just processing what I'm saying here. I think you should. I think you should sit down before the test and really think about what I'm saying. If the black and the red in this picture over here are not parallel, then we can truly say that the red line is not perpendicular to the plane. Okay? The second drawing is we've got this plane and a flagpole sticking out, right? And we have this line. We're suspecting, well, or at least wondering, is the line R of t perpendicular to the flagpole? You know, so we'll pick a little vector in here called L. Is L perpendicular to the flagpole N? If so, the dot product would be 0. Well, we show that that isn't the case either. That's not the case. It turned out we didn't get 0, we got 2, remember, down here at the bottom. So this just means that we're not dealing with this case either. And if the red line and the black line are not perpendicular, then we know that the red line and the black plane are not parallel. Okay, and the last thing you might be confused by is I use the word parallel test here and orthogonal test here, or perpendicular, you know. Those titles are for the vectors. The final conclusion for the parallel test was that the line is not perpendicular to the plane, and the final conclusion for the orthogonal test is the line is not parallel to the plane. So that one takes quite a bit of thinking. None of it was hard mechanically, but a little bit of sketching and trying to figure out what it means. And if you have any questions, you can ask about this in class, and it will be on your worksheet anyway. So, thank you for the patience during that long lesson.